All right, we'll go ahead and get started. Welcome to Webinar Wednesday for June. My name is Kelly Huff. I am the marketing manager for Veritech Solutions across all of our offices in the Southwest. And we have a guest presenter today, Janice Means. She is Professor Emerita of Lawrence Technological University. And before I turn it over to her, just a few housekeeping notes. We are recording this, so we'll be able to share that later. Janice, if that is okay with you.
Certainly.
Okay, should have asked you that part first. If you have any questions, go ahead and put them in the chat and we will go over them at the end of this. And if you are looking for a PDH certificate, just make sure that your name is shown when you look at the participants is something that I can figure out. If you have a common name like John or Dan, just make sure you include the last name because there's quite a few of those. If I can't figure it out, I will be sending you a message in the chat, so just pay attention to that. And with that, I think I covered everything. Janice, I will turn it over to you and give you as much time as you need. All
Okay, thank you
right.
very
Thank you,
much. And
Janice.
I would like to thank Veritech, Dan and Kelly especially for the invitation to speak. And I want to add one more thing. I do number my slides, so if you have a question, if you want to refer to a slide number, we can go back to that slide as necessary. So today I'm going to be talking about climate change, myths and reality, and I'm going to concentrate on a case study for Southwest United States, which is including these 6 states shown in the corner. So I have some learning objectives stated here, and I'll give you a minute or so to read them. These are things that I hope that you'll come away with once we're done. Okay. And I'd also like to make some acknowledgments. I want to thank the climatologists that I worked with on the climate change chapter for ASHRAE's Handbook of Fundamentals. I learned so much from all of these people. Most of the people on my committee were PhDs. I don't have a PhD, I have a master's, so I was very impressed with what they had to offer. Okay, so as an agenda, we're going to start with an introduction. Is climate change real? And then we'll go into answering the question, is today's climate change anthropogenic? In other words, is it caused by humans? Is this a myth or reality? And finally, the third part, rather, is I'm going to talk about the present potential future climate outcomes, not only for the whole world, but also the United States, and in particular, a case study for U.S. Southwest. And then just briefly talk about what we can do about it. This presentation doesn't give me enough time to really get into mitigation, adaptation, and resilience, but these are things that we definitely can do about climate change. Then I have some concluding remarks. So I'll begin. To begin, I always like, as a professor especially, to define my terms. And so let's look for a definition for climate change. The IPCC defines it as a change in the state of climate. And notice this, it's identified by two particular things, by changes in the mean or variability of its properties, and probably even more important is it persists over an extended period of time, typically decades or longer. So climate change and weather are different. Weather is what you experience when you go outside and you feel the temperature, maybe some precipitation, the humidity, what have you. But climate change, again, is over a period of time, the variability in these properties. Okay, so what are some signs of climate change? Well, first of all, the increasing pattern of record high global temperatures, as shown here. In fact, if you look at the background behind me, this is another representation of this using colors. As all of you are very aware, I'm sure, it's 2025 was the hottest year recorded, and the last 10 years have been the hottest ever on record. Sadly, it may be the coolest year when we look back from here forward. Signs of climate change again. Arctic sea ice is decreasing very rapidly. This is a chart just going from 1980 to our present time, and it's showing how the ice uh, decreases and increases as it does every season, but it's a downward trend. And during the uh, last decade, or excuse me, it's now down about 12.2% per decade when we compare it from 1981 to 2010. So this part right here. So in 1980, there was 1.86 trillion acres of ice, which you can see in this diagram here. In 2022, it had decreased significantly to 1.5 trillion acres. And then in 2024, it was down to 1.06 trillion acres. And why does that make a difference? Well, as it decreases, more dark colored blue water shows up, which means more heat is absorbed, and that increases the melting. And why else? We'll talk about a little bit more in just a couple of slides. Glaciers worldwide are shrinking or disappearing. And when glaciers uh, go back, we get sea level rise if it's from the land and going into the ocean. Water availability becomes a problem. Hydroelectric plant operations have problems. You see reservoirs going down, and the safety of those living near glaciers is a problem. Just last week, there was an avalanche, for example, in Switzerland, which devastated some of the houses below it. And this is happening more and more often. The Columbia ice fields, I first went to the Columbia ice fields in 1975 when I was driving the Alcan Highway. And the next time I saw them was 1986, I think it was. And my husband was driving and he said, "Oh, we're at the Columbia ice fields." And I said, "No, we're not. We're not there yet. It doesn't look anything like what I remember." And we were there. It had changed so drastically. I was there again in 2017 and noticed that there were these posters up. In 1990, this is what the glacier looked like. And this was what it was a few years prior to 2017 when they made this slide. It has changed so radically. In fact, the Mendenhall Glacier in Alaska, which I visited in the early 2000s, uh, didn't used to allow anyone to build within a mile of the glacier. Now they're allowing people to build because, as you can see from these diagrams, the glacier is greatly receding. In this diagram, the green represents forest, the dark blue is water, liquid water, and the light blue is the ice. You can see on August 17th where the glacier ended as opposed to 20, and I can't see it on my screen, 2080 or January 28th of 2023. You can see how it has receded. What really got to me when I was there is after they showed a movie of how things had changed, I noticed that there was a blackboard up and they were recording daily changes in the glacier, daily. So it's happening very rapidly. Another sign, or excuse, one of the causes, I should say, or one of the results of the glaciers and the ice sheets melting is we get global mean sea level rise. As of January 25th, the sea level overall had risen 10.24 inches. And it's not all over the world at the same, it varies a bit. But it's interesting. In 2024, it was higher, and actually the rate of increase was also higher, and this was unexpected. They think that it was because of El Nino. El Nino, as you may recall, is a periodic weather event, if you will, that happens that causes our temperatures to be a bit higher. So, it's likely to rise from 1 to 6.6 feet above the year 2000 levels by 2100. There are predictions for later times that this could be as high as 30 feet. So it does make a big difference. Also, for anyone interested, there is a NASA sea level projection tool, which I thought was kind of fascinating. You can go to it and you can click on any of these dots and find out what the latest prediction is or what is happening as far as sea level rise goes. So, what are some of the weather signs of climate change? And these were all predicted by climatologists. I have been lecturing on climate change since the early 2000s, and I was amazed at how rapidly things were starting to occur with some of these extreme weather events. They're more intensive, they're more frequent, and they're more extensive. And what are these? The wildfires, the heat waves, the drought, storms of all different variety, and also floods. So why is it important, or why do I think it's important that everyone become climate change literate? And one of the reasons that I do presentations on this is this. It's existential. It's happening now. It's not something in the future, and it's something we can do something about. In 1960, since 1960, CO2 levels, carbon dioxide levels, have increased 100 times faster than any natural cycle following an ice age. And you're going to see this through some of the charts that I'm going to show. We need to have this knowledge if we're going to act, if we're going to be able to educate our policymakers to make a difference in this. We need to pass it on. So please talk about climate change. ASHRAE has said in the position document that climate change is the most formidable environmental challenge ever faced by society. I'm on the committee that's rewriting or updating the ASHRAE position document on climate change, and we certainly are keeping this quote. Okay, so the next section, I want to talk about, is today's climate change anthropogenic? In other words, is it human caused? Is this a myth or reality? Is it caused by natural forces? Let's look at some of the natural forces that you might have read about on the internet, for example, that say that this is the reason for the increase in temperature. Let's see if it's really true. Let's look at solar activity. On this chart, which starts in 1880 and goes through 2020, we can see on the left side and in yellow, the irradiance from the sun. And on the right side, we can see the temperature rise in red. If you look at everything up until 1960, you could say, yes, seems to be a correlation between irradiance and temperature increase. But after 1960, you see these two lines diversing greatly. So we cannot say that solar activity is causing climate change. So is there another natural force? For example, volcanoes. Actually, and I will show this in a few slides, the particulates and the sodium dioxide that's emitted from volcanoes provide a cooling effect. And the CO2 emitted is only 1% of that released by human activities when we're talking on an annual basis. And for anyone that's interested, I thought this was interesting to go through the slides, or excuse me, go through the different components that go in a volcano, which does have a lot of ash coming up. Not all of them do, so not all of them are as effective in causing the cooling. But this goes through the chemical reactions that take place, which I thought you might be interested. I've even included what the all of the chemical terms are. One thing that you should note is that nearly all of the gas molecules ejected are water, CO2, and sodium dioxide. So the sodium dioxide seems to have the biggest imprint on making it, shadowing, if you will, the sun, changing the albedo. So, what about submarine underwater volcanoes? And underwater volcanoes, some people have said, "Oh yeah, that's what's causing the ocean to heat up." And that's not true. There's no evidence that that the number of volcanoes erupting is increasing. There is evidence that we have noted or registered that there are more volcanoes underwater, but they're not active. Also, it intuitively you would think that if the underwater volcanoes are warming the ocean, that it would warm it from the bottom and going up. But when you look at the temperatures in the oceans, it's the surface water that's the hottest, not the deep water. So there was a unique eruption that occurred in 2022 in January, the Hunga Tunga Hunga Ha'apai. I challenge you to say that 3 times without slipping up, occurred, and it was one of the largest submarine ones in recorded history. And also, it turned out not to have a big effect, even though there were several people on the internet, especially, it said, oh, this is going to have a big effect because it emitted more water into the stratosphere than they'd ever seen. It was up to 15% of the total water in the atmosphere was added from this volcano. What happened was they found out it did not have an effect on temperature or climate change, mostly because water dissipates very quickly once it's in the atmosphere. However, it did have an effect on the ozone layer hole. And some of you may be very familiar with how we have changed the refrigerants that we're using so that they don't cause the increase of the ozone hole in the Antarctic. But anyway, it caused that to temporarily increase, and now it's gone back to closer to where it was. So let's get back to volcanic eruptions and how they affect climate. They really don't affect climate, but they do affect weather. And here's another plot of the temperature from 1880 through 2020. It's in degrees centigrade, but I think we're looking at it relatively so we don't have to worry about it. The Lola's smoothing is what the dark line is, and the annual mean is shown as going up and down. As you all know, many natural things don't follow straight lines, they go up and down. Any case, I plotted different volcanoes that have occurred, and on each of these, you can see that the temperature went down. The largest volcano to go off was in the 20th century was in 1912, the Navaruta in Alaska. And look at how much cooling we've had. There were 3 volcanoes here, and this one had the biggest effect. Going on, there were some that occurred erupted multiple times, and I've shown as 2 arrows here, for example. Uh, Kilauea was like that. It went over time, the one I just had right there. Um, Mount St. Helens didn't have that big an effect, but it did have an effect. El Chichon had a bigger effect on the weather. Mount Pinatubo was the second biggest in the 20th century, but you can see it did not cause as much cooling as the Navarupta did. So it probably didn't put as much ash into the air, even though it was the second largest volcanic eruption. And I stumble over speaking this, so forgive me if I mess it up. The Eyjafjallajökull in Alaska occurred in 2010, and I'm very familiar with this one because I was presenting at a climate conference, Klima 2010 in Turkey at that time, and I got the last plane out before they stopped flying because of the volcanic ash in the sky. So as you can see, volcanoes are actually our friend in a certain sort of strange way in that they provide some at least temporary cooling, and it's only for 2 or 3 years. So, what about natural cycles? You hear a lot saying, oh, it's just natural that we're going through this cycle. The Milankovitch cycle is probably the most well-known and has the biggest effect, and as I understand it, on our climate. The cycle has to do with the orbit around the orbit that the Earth takes around the sun. Sometimes it's more elliptical and sometimes it's more circular. And as that changes, we go through ice ages, for example. That is also coupled in part of this cycle with the wobbling of the axis that our Earth turns on. So if we look at the records of these, and I'll explain that in just a moment, we can see that the CO2 levels also vary with this. So this is a plot from 800,000 years ago to present day, along with the temperature, which is in the lighter blue, and the carbon dioxide values, which is in the darker blue. And as you can see, we've had 8 ice ages along this. You're probably wondering, well, how do we know what the temperature and the CO2 was 800,000 years ago? Well, they do ice cores, and when they take those cores, they can analyze what was in the atmosphere at the time. There are also other ways that have been developed to do this, more recent using the rings in a tree, for example. In any case, you can see that the CO2 and temperature varies pretty much directly. If we also look at global mean sea level, and this chart is pretty close to that one in time. It's 771K years ago to today. And if we were able to put this chart over this other one, I think you can see they're pretty much going together. So as the CO2 increased or decreased, so went the temperature and the global mean sea level. So let's look in particular about CO2 levels over the last 800,000 years. This is another chart similar to the last one. On this one, it's showing the CO2 levels. And as you can see, done in yellow is the ice core data, and the red is the modern day instrumentation data. So what's interesting about this, all this 800,000 years, the level of carbon dioxide in the atmosphere did not exceed 300 parts per million. Then in 1911 was the first time that 300 parts per million were exceeded in this 800,000 years. In May 9th, a little bit over 100 years later, it was 100 parts per million higher. So it went from 280 to 300. From 300 to 400, it went in 100 years. And this is most likely not been exceeded in 3 million years of Earth's history. But it got worse. The rise from the mid-19th century, and you're going to hear me repeat this several times, was 10 times faster increase in CO2. And if we look just since the year 1960, it was 100 times faster than what it had been from any natural time. And if you look at the pattern of these, it looks to me like instead of going up, we might go up a little bit, but it seems like we should be starting back down, doesn't it? If this was a natural cycle. Also, I recorded or listed the amount of parts per million of CO2 from May 16th of 2025. It was 430.51 parts per million. But the CO2 levels vary. And this chart shows it very well. This is only from just before 2020 through 2025, where it's showing the different values of CO2. It's taken at Mauna Loa, which in Hawaii, which is at about a 20-degree north latitude. And this is the average on the black. The red indicates what's happening through the months. And if you see, if you're starting out in January here, as the winter goes on, you get higher and higher carbon dioxide levels. But as we approach spring and summer, it falls back down. Why is that? Well, trees absorb the carbon dioxide, and the northern hemisphere has a larger land mass, therefore has more trees on it, and even more than when we compare it to the Amazon rainforest of South America. So we get these going up and down. So this number that I've given you, 430.51, will probably continue to increase, and then it'll start going down a little bit December. But the tendency overall is to keep going up. Where temperature increases, if we look at global temperatures from 1850 to 2024, there are, like, say, 6 different measures that have been taken by different groups for this. So you do see some variance, but pretty much they're pretty reliable. But they do vary depending on how they're measured and who's measuring, where they're measuring them. We've had unprecedented warming since 1880 from here on. As I mentioned before, from 1880 to present, it's 10 times faster. But if we look from 1960 on, look at the big difference here. It's 100 times faster than it was uh, during any other time when it was warming up after an ice age. So in 2022, the Earth's temperature was at 1.1 degrees centigrade or 2.3 degrees Fahrenheit, higher because it's a relative amount than the 1850 to 1990. And this is from IPCC. In 2024, as all of you know, it was the hottest year on record. And depending on which group you listen to, it was right around 1.5 degrees centigrade or centigrade degrees. I'm using the 1.47 from NASA on that, but you will hear values slightly higher or slightly lower than 1.5. Again, I want to recognize or have you recognize that this doesn't mean that the 1.5 degrees Celsius that the IPCC has specified as sort of a landmark, if you will, or not to be our limit that we wanted to keep it to, is not measured for 1 year. It's measured over a longer period of time, 20, 30 years. Okay. So again, I just want to emphasize these highest temperatures varies by source. There are other charts you can look at. I thought you might find interesting. If you go to climatelevels.org, there are several charts, more than the 3 I've listed here. But what's neat about these is you can click on any point on the chart and it actually gives you a value. And this one's for CO2 levels, global temperature record, and then global sea level. So the Earth's rising temperature is directly related to an increase of carbon dioxide in the atmosphere. I think you can agree with that from what I've shown, but why would that cause warming? And how do we have any idea? Well, we can thank actually a woman named Eunice Newton Foote, who in the mid 1800s did some experimentations with jars having CO2 and CO2 with moisture in different jars and set them in the sun, and she recorded the temperatures. And she came up with a conclusion that when CO2 is in the atmosphere, it can cause warming, and it's hard for it to cool down at a very fast rate. By the way, Eunice Newton Foote did not get credit for her experimentation until this century. I think it was like, I don't remember the exact year, 2010 or something, because a man had gotten the value, and they finally found some records where she had done the research and wasn't able to present it. It was presented by a man because women weren't allowed to present, but I thought that was interesting. So, why do we call it the greenhouse effect? Well, it's kind of like having a greenhouse. What does a greenhouse have around it? Water, or excuse me, not water, glass, glazing. So when the sun's rays, the sun irradiations comes in short wavelengths, okay? It's able to go through glazing and through the greenhouse gases, okay? But when it reaches the earth and heats up, it turns into long wave radiation, which is blocked by glazing in a greenhouse and blocked similarly by greenhouse gases. So this is why we get the increase in temperature. So we have both the greenhouse gases and we also have something called solar albedo. The albedo refers to the fraction of sunlight reflected by a body. And when these two items are not, or two contributors are not equal, we're going to get an imbalance. So let's look at these. We have greenhouse gases that cause the global heating for many, many causes here, anywhere from natural causes like to a minimal amount, volcanoes, also from uh, the frost melting in the north and releasing methane, for example. So, what are the greenhouse gases? Water is the most largest contributor. Carbon dioxide, methane, nitrous oxide, ozone, and fluorinated gases. Water, we don't hear too much about. We hear more about CO2 for the reason that the water doesn't stay in the atmosphere as long. It dissipates quickly, even though you probably will have heard that the amount of water in the atmosphere has been increasing overall, and that's part of the reason we have our it dumps so much water in storms. But in any case, we have all of these things going on. I'll explain the rest of them in a moment. That provides the global heating. Then for the reflection is caused by clouds and snow, and to a greater degree, as you saw from the volcanic eruptions or some volcanic eruptions. When these are not equal, we get what's called radiative imbalance. Okay. And so that's what's happening here. So what I'm proposing here is the most significant input for the greenhouse gases are human caused. So what are these? Well, change in land use, the elimination of forest, the burning of fossil fuels to provide our transportation, to heat, cool, and ventilate our homes and buildings, to run our factories, the change in agriculture and agricultural methods. The food that we eat since 1960, we've eaten even more beef, for example. So cows and sheep are what are called ruminators, and they create a lot of methane that goes into the air. And then we have the fluorinated gases that escape. So is this actually the case? Are the humans doing this? What evidence do we have of that? So let's look at this natural or human and natural influence on global temperature. First, let's look at the natural causes. The natural causes are in blue here. And again, like everything else, it varies in the range that's predicted, or so you're going to see the average shown in the dark line. Human drivers are in red. When you combine the human with the natural drivers, you can see that is in yellow here. And if you look what is actually observed, which is in black, you can see that it pretty much goes along with what humans have done. Okay, so there's one thing to show how it works. What about, or let's look at carbon isotopes. This is very interesting, and uh, not to get too technical for those of you that might not be into chemistry, but carbon has a weight of 12, meaning it has 6 neutrons and 6 protons in its nucleus. There are a couple of isotopes that we want to talk about. One is C13, which has an extra neutron in it, and carbon 14, which has 2 extra neutrons. And I'm sure all of you have heard about carbon 14 dating. The reason that we can use carbon-14 dating is as an organic matter gets older, it loses some of these neutrons, which then can be calibrated to the date that they're old. Now, when we talk about fossil fuels are fossil fuels. They're old. They have no carbon-14 and they have very little carbon-13. So we can look at our atmosphere and look at the relative amounts of carbon-12, carbon-13, and carbon-14. Before we do that, let's first note that CO2 levels have greatly increased, as you have seen. They're 40% higher in 2019 than in the 19th century, and 50% higher today than in the 19th century. But when we analyze what's in the atmosphere, the fraction of isotopes for C14 and C13 have significantly decreased, even though CO2 levels have increased. This shows or gives proof that the majority of CO2 in the atmosphere is from fossil fuels. So, the IPCC has been studying this over a number of years. On the right, you can see a chart where it shows each year when it had uh, when it issued a report, and you can see in 1990 they didn't blame humans for anything, and then as they gathered more and more information, they finally came to the conclusion on the left, quote, "It is unequivocal that human influence had warmed the atmosphere, ocean, and land." This is a partial list of the worldwide scientific societies that concur that climate change was caused by human action. It's not a complete list, and I accessed it in 23. I'm not sure when it was developed. It was done by the Canadian government. And ASHRAE's not listed on here, but I'm sure they're one. So there's a lot more societies that have held this position. Okay, so now let's get into present and potential future climatic outcomes. Climate zones are on the move, and they're changing at an alarming rate. Plants cannot react quickly enough to these. Animals can move a bit, as long as they can find a cooler place if they need a cooler place as temperatures increase. This is a diagram showing the climate zones. It's ASHRAE map. 8 is the coldest zone, with 0 being the warmest. By the way, the 0 climate zone was only added because this part of the world around the equator was getting so much hotter. In addition to that, climate zones are, especially in North America and Europe, moving at a faster rate north. Okay. So the global temperature, if we average it over the last 30 years, not just last year, but over the last 30 years, it's increased about 1.34 centigrade degrees. And that's since the 19th century. And it's expected, as we all know, to increase further. So, by the way, if you want to look at the different climate maps, they're available free of charge at ASHRAE at this site. Okay, the Meteorological Organization recorded 150 significant global climate disasters. This is extreme weather events in 2024. And these include the following: more frequent heat waves. As we know, in the US, we had the hottest temperature since 1880 for 2024. And there were severe heat waves in all around the world. One that I find really astounded me is in 2023, the Atlantic Ocean near Florida had water temperatures exceeding 100 degrees Fahrenheit. 100 degrees with the ocean. We're getting extreme rainfall and flooding in several areas of the world. I've listed them here. Drought in several areas, including our Southwest US. Record deadly fires. I'm sure you've heard about all of these on the news. Extreme weather events are expensive. To me, it's much more expensive to not do something about climate change than it is to ignore it. And here's some examples. I'm going to give you these examples in 2024 cost in US dollars, and these exceeded those of 2023 for global national disasters. There were losses of 320 billion with a B. Total insured losses, it was the third most expensive year and the fifth most costly since 1980. 140 billion dollars of the US losses were uninsured. Insurance companies are either pulling insurance from areas that are often hit by these extreme weathers, or they are charging such exorbitant amounts to cover them, people can't afford it. Canada experienced the highest losses ever since 1980. That was at $10 billion, with only 60% of that being insured. Brazil's Rio Grande do Sul state had flood damages of $7 billion, and only $2 billion of that was insured. So lots of heavy losses monetarily. So there's more to it, though, than monetary losses, isn't there? We have people dying from this. I'll show you some numbers in a few minutes. Their homes are being destroyed, communities are being destroyed. There's food insecurity, and as temperatures heat up and climates change, there's going to be less food. There are more health issues, and there's more and more research being done on that. The biodiversity of animals and plants is going down, which is not good for us as humans. Who is hit the worst? Who has the greatest risk? The young, elderly, and the poor. And many cases, this includes the minorities and indigenous populations, as well as people in poorer nations, which contributed less to the problem than some of us, like in the US, but they have the least ability to, find the resources to adapt to climate change. So, worldwide, if you are interested, I listed three sources of from around the world where they're looking at climate change outcomes. Now, I'm going to talk about a case study for key and present and potential future climate outcomes. I'm going to start with the United States, but I'm going to emphasize the southwestern 6 states identified earlier. So, climate zones I already mentioned were on the move in the U, and here it is in the United States. And climate zones have moved about 200 miles north in North America. 200 miles. It's changing rapidly. I don't know about you. I know I see birds, for example, that I've never seen before, that I would only see if I went to Ohio or further south. I'm seeing them now in Michigan. Here is a detail from the Southwest, and as you can see, these uh, positive marks actually refer to where the climate zone has increased. So, for example, in this yellow, which would be zone one, it has gone up into what was originally zone two around, and some areas are worse than others. But every state that we're talking about now has had increased temperatures, and so their climate zones have changed. So let's look at average summer temperatures. Well, they're increasing throughout the United States. On this chart, the very dark red means that the summer warming has, since 1970, has increased by 5 degrees or more. The next bright red is it's between 4 and 5 degrees more, and then we go down as it goes. In the Southwest, we see some very heavy increase in temperatures. Whoops, sorry. And you can see, especially in southern, or actually mid to southern New Mexico, parts of Arizona, parts of California, Nevada, Utah, and to a smaller degree in Colorado, but they all show increases. The number of days temperatures exceeded 95 percentile, and this is taken between 1948 and 2023, is shown on this chart of the United States. Moving all the way to the right, the red triangle pointing up, the largest one, means there are more than 25 days that the temperature has exceeded the 95% percentile relative to 1948. The smaller triangles in red show to a lesser degree. Zeros, which covers most of the United States, shows five or fewer to five more dates. And then the upside down triangles in blue show a decrease in the days. And you can see that there's more increases than decreases, especially when we look at the Southwest. So it has Southwest, as you can see, has the greatest number of areas with hotter temperatures, and these temperatures are lasting longer. Let's talk about drought. And this particular map, this shows all of Western United States, but you can see very clearly using this chart here that the darker red is showing that New Mexico, Nevada, Colorado are currently in extreme drought. Okay. And this drought is expected to increase in area and severity. In fact, it has. To maybe so that you can read this chart a little bit easier, I've enlarged it over here. So let's look at this. This first column shows the percent currently that is in drought. It's showing it as 28.5% roughly, whereas 1 year ago, over 60% was not in drought. I actually figured out the percentages here. The decrease in the areas where there was no drought is almost half or 50%. If we look at the yellow is the abnormally dry area, and yellow's on here, and we see that it has increased by 55%. The beige is moderate drought, has increased by 35%. The severe drought, which is in the orange, has increased 18%. The severe, or excuse me, extreme drought in red is increased 10%, and the exceptional drought has increased 9%. And again, those are the percent areas on this. But in every case, you can see that at least the southern part of the mid or of the Southwest has been severely affected by drought. And I'm sure I'm not telling anybody from that area anything new on that. So let's look at fire weather. Drought obviously also leads to wildfires, and for a couple of reasons I'll get into a little bit later. But this is the annual fire weather days. Okay, that means that days that are hot, dry, and windy between 1973 and 2024. And if you look at the darkest, excuse me, at the darkest numbers here, you can see that it's increased by over 56 days. The next red is over 28, and the lesser red is 14. And if again, let's look at particularly at these 6 states that we're analyzing. There's a lot of dark red in here. By the way, these white, or I'm not sure if they're white or this sort of light gray. It's hard to tell on here. The light gray means there's no data. The white means there's 0 weather days. I strongly suspect that in this area that these are actually where they can't find data. It makes sense to me, but I don't know that for sure because it's hard to tell with the colors. So much, as you can see, of the Southwest states have 28 to over 56 fire weather days. So let's look for the projection just for this summer, and it's already starting to get pretty hot. Okay, so on this one, and I've enlarged this scale again so you can see it, it's giving percent chance or probability that the temperature would be above normal. So the least on this is there's a third to 40% chance that it'll be higher temperature for this is summer of this year. For the beige, the next one here, which is shown through part of the excuse me, part of the southeast and part of the west as well, is showing 40 to 50% probability. The next one, which covers a lot of what area we're talking about right now, is 50 to 60%, and then 60 to 70%. So that is the probability and percentages that we are going to have above normal temperatures for this summer. There's a similar one for precipitation, and I'm sorry, I got a typo here. That should be a small I, not a large I. In any case, the precipitation doesn't look as bad. There are equal chances that there would be more or less precipitation through much of the Southwest. Partly that there would be 33 to 40% below normal precipitation. But then I thought this is interesting. In Arizona, it's showing that a good portion of it would be possibly above 40 to 50% above normal. So maybe there will be some flooding, who knows? Okay, so what I want to show next is NOAA's National Centers for Environmental Information data on billion-dollar, and that's with a B, weather and climate disasters. Now, between 1980 and 2024, the US government kept track of extreme weather events, but only if each event that was over $1 billion in cost. Okay. The total events for this 44-year period were 403 with deaths exceeding or just under 17,000 deaths. What I find interesting here and is pertinent to the Southwest with drought conditions is that 27.5% of the deaths listed here were due to heat waves during drought. So it's important for us to make changes in our buildings so that we don't have as many people dying from heat. Heat kills more people than cold. The cumulative cost in billions of dollars was $2,918 billion, or if you will, nearly $3 trillion. The average events, if we look over the 44-year period, there was an average of 9 events per year. But look at this, between 22 and 24, there were 24.3 events per year. So the number of extreme events has gone up. Below are the different types of events that were monitored and showing the numbers of them. Severe storm events had the greatest number, and the second was for a flood and then drought. Now I'm going to show the 6 states that we're looking at, Arizona, and then Mexico, Utah, Colorado, Nevada, and California. And I'm showing the number of total events for each. Let me caution you that you can't just add these up and see what percentage of the total they were, because some of these events that were counted in this number of 403 occurred over several states. So so you have a highlight of what that is. Colorado had the greatest number of extreme events, followed by, as I say, Colorado had the greatest number, followed by California. The cumulative costs are shown here. California had the highest cost, Colorado the second. And the average events per year, when we compare it for the period since 1980 to that of the last 2 years, in every case, the number of events has increased, in some cases more than twice. So let's look at the specific events that are affecting the Southwest. Drought is definitely high in the numbers. In Arizona, it's the second highest would be wildfire events. When we look at New Mexico, it's also the highest is drought, second is wildfire. Utah, The drought events, the wildfire events almost are equal. It's 10 as opposed to 12 drought events. Colorado is very different. They had 16 drought events, but they had 42 severe storm events and 12 wildfires. So Colorado is most concerned about the severe storm events. Nevada, uh, again, it's similar to Utah, and it had 13 drought events and 11 wildfire events. California is a bit different. Again, they had the drought is 14. They had the largest number of wildfire events of 19. So you see, whereas it does change depending on the state, overall, drought is the most common event for if you look at all 6 states. It's unfortunate that this data is no longer being kept by the government, but you can look at the historical data, and there are all sorts of charts. You can see it on a monthly basis, what have you, if you go to this source. Okay, so in the Southwest, climate change causes what? It causes a reduction in the availability of water, and that goes for both surface and groundwater. Why is this? Well, there's less snow falling, there's less rain falling. Snow that does fall melts earlier than normal. You have reduced river flows. By the way, it's all happening all over the world. Lower lake levels, lower reservoir levels. Temperatures are going to be increasing, and heat waves are going to last longer. Prolonged and more intense drought, increased aridity. Wildfires will be increasing, and they're going to burn hotter. And why is that? Well, obviously because of increased heat and drought, but also the number of dry, dead trees are increasing. And mostly this is caused, well, not only by loss of water, but it's caused by invasive species killing them off. This is most prominent in Colorado, and it's been true for many years now. The pine beetle, which used to die out with the colder temperatures, the temperatures aren't getting as cold. And so the pine beetle is devastating the pine trees. So you have these dead trees, you have the increased heat, you might have some lightning or somehow fire, and you get a wildfire. Air quality is declining. And this is due to wildfires and as well as dust in the Southwest. You don't even have to be close to the wildfires. I live in Michigan, and there were wildfires the last couple of weeks in Manitoba. Detroit had the worst air quality of anywhere in the world, not because there was a wildfire close to us, but because of Manitoba, and that was 2 weeks ago. People's health will decline, obviously from the temperatures, but also the increase in dust, insect pest, and plant diseases. There's been more recent research being done on why or how pests are increasing. Part of it is pests that normally were at lower, hotter environments are now moving north or south, depending on where they are relative to the equator. There's increased intermittent flooding and mud flows. This is particularly true in California, but if you look just past week in Kentucky, for example, and I think also Texas, even though we're talking about the Southwest, you're going to have more flooding and mud flows. Reduced food production capabilities when you have the weather changing so rapidly. The crops cannot be maintained. Crops are differing where they can grow. By the way, if you look at wine, for example, the UK is becoming a wine place because their temperatures have increased. But it also affects animals. We have reduced water, increased plant and animal disease. So, what do we do about it? And I wish I had more time to talk about this, but there are 3 things we can do. We can mitigate, meaning that we want to avoid the unmanageable, and we can do that by replacing our fossil fuel sources with renewable sources, decarbonizing, and using carbon sequestration. We can adapt by managing the unavoidable with the design of our buildings, the grounds around them, the infrastructure. ASHRAE is leading on this, but other groups such as ASME, civil engineers, all are coming up with solutions that we have. We have the solutions, we just have to use them. We need to make our buildings more resilient, and that includes protecting people, buildings, and equipment. Some ideas are providing refuge areas or more resilient refuge areas. If you might have flooding, making sure that the equipment's located where it won't be affected by flooding. And there's so much more to this. Okay, so in conclusion, climate change is not a myth. It's it's occurring now, and it is of an order of magnitude faster than the last 20,000 years, with CO2 increasing 2 orders of magnitude faster since 1960. It's primarily caused by human activities since the mid 20th century, although it started before that. Think I convinced you of that. And we must use the strategies I've mentioned to take care of it, to mitigate it, to adapt to it, and make our buildings resilient. And ASHRAE's 2025 Fundamental Handbook, climate change chapter does offer some trade-offs between mitigation and adaptation. And that should be out any day now. The 2021 edition had the original chapter that we wrote. I'm the chair for the handbook for climate change chapter, so I'm very intimate with what goes into there. Not addressing climate change is costly. I've shown you it's cost not only in money, but people's lives, extinction of animals and plants. There's so many problems caused by it. And the poor, the minority, the indigenous, especially young and elderly, are the most affected by climate change. Yes, we're in crisis, but there's still hope. I can't stop without giving you some good things that are going on. More and more organizations, businesses, and countries are acting, and states in the United States also, to mitigate uh, climate change. And these include, as an example, in the United Kingdom, they're mandating that all new homes have solar panels by 2027. Renewable energy costs, I'm sure you're very aware, has gone significantly down. It is now less expensive to build a solar plant than it is a coal plant. And the solar doesn't release CO2 and has less maintenance costs. Research is being done and a lot of experimentation on how to capture and sequester carbon dioxide, as well as produce new products for it. We can move to safer locations. I always hate to hear people rebuilding in an area that has flooded so many times, for example. We know how to adapt our buildings to provide greater safety and resilience. We know how to use our energy more efficiently and to convert to renewable energy sources. So if we act now, things may not be better, but they should not get worse. Now, we may slip over the 1.5 degrees centigrade for a while, but using carbon sequestration, we should be able to pull it back and at least maintain our our home, our world, hopefully, so that it's still livable for us. Thank you so very much for this. I will entertain questions, and just so you know, the colors at the bottom show how much the temperature has increased from the 1800s through now. Thank you so much. And I
Thank
will
you,
now
Janice.
entertain questions.
Yes, thank you, Janice. All right, so there are no questions in the chat. So if anybody
Really?
does, if anybody does still want to put any questions in there, feel free to. You can also come off mute and ask your questions or have a discussion that way. Just a quick thing, I launched a poll towards the end. I'd
Okay.
love to get some feedback from everybody on here. So before you jump off, I'd love for you to answer some of those questions. But yeah, if there's any questions, an excellent presentation.
Thank
There's
you.
comments.
Any comments?
Yep, just excellent presentation.
Oh, that was what you were
Yep,
saying. Thank you.
that was the comment.
Thank you so much. If anybody does have questions that you think of later, you're welcome to email me at jmeans@ltu.edu, and I'd be glad to offer, answers for them. I also will be attending the ASHRAE conference in Phoenix, which I'll be there from Friday through Wednesday of Friday of this week through Wednesday of next week. So feel free to contact me.
All right, Dan, do you have any closing
No,
remarks?
no. Janice, thank you so much for your presentation and building this, especially for today's event, and your support of ASHRAE and getting this information out into our community.
Thank you, Dan. I
And
appreciate that.
we do have a question. Could some of the money, um, could some of the dollar value increase in damages be attributed to our build out in new areas?
Yes, that is true. People are building closer to forests, for example, and there's more. If you look at the way people are moving, they're moving, for example, to Florida, where along the coast. So there is a problem. And also, I don't think I mentioned it, but if you're looking at the cost and something occurs in an area where there are very few people, you're going to have a low cost. That doesn't mean it isn't having the extreme weather. So that kind of fits into it. Excellent question.
All right, great details, Janice. Thank you. This comment.
You're welcome. Thank you. Excellent.
All right,
Again, thank you so much, Janice, and I look forward to seeing you here in Phoenix.
Okay, I look
absolutely.
forward to being there, not for the heat, but I look forward to seeing all my ASHRAE buddies.
Yes,
You
Take
won't
it
care.
need
will
a
be warm.
jacket.
Thanks. Take care.
All right, we'll see you soon. And I will follow up with an email to everybody on here with PDH certs and some follow-up information. So in the meantime, if you have any questions, you can reach out to Dan or myself or to Janice directly, and we'll be glad to continue the discussion. And we'll see you next month. Oh,
Stay
no,
safe.
we'll see you in August. We're taking July off. All
Thank
right,
you.
Take care.
thanks.
Bye-bye
Bye.
now.